Welcome, curious minds, to another deep dive.
Great to be here.
Today we're presented by Knowledge Flow, and we're embarking on a journey into one of the most foundational, really influential languages in computer science, C++ programming.
It really is a cornerstone, isn't it?
Absolutely. Our mission today, well, it's to give you a swift but also thorough navigation of C++ core principles and, some truly surprising features too. We're going to build your understanding from the ground up, really starting with those fundamental building blocks that make C++ such a powerhouse.
Yeah, the essentials.
Exactly.
Yeah.
From its origins, its basic structure, to how it handles data, controls program flow, and then we'll get into the advanced object-oriented stuff, inheritance, polymorphism. We're going to unpack why C++ is still so relevant, so powerful today.
And what's truly fascinating here, I think, is C++ unparalleled role. It's like a cornerstone language. Its concepts, they aren't just stuck in C++ wool. They deeply influence, they underpin so many modern programming languages, systems you encounter daily, often without even realizing it.
That's a great point.
So this deep dive, it's really designed to equip you with a solid, actionable understanding of C++ key elements, building a robust mental model of how it operates.
Without getting totally bogged down in every tiny detail.
Exactly. It's more about gaining insight into its design philosophy, its practical application.
That's spot on. So, okay, let's get right into it, because this is where it gets really interesting. The genesis, the fundamental anatomy of C++.
The origins.
Yeah. This wasn't a language that just, poof, appeared overnight, right? It was a very deliberate evolution. It began its life back in the early 1980s, developed by the brilliant Bjarne Stroustrup, and specifically at AT&T Bell Labs, right here in the USA.
A legendary place for computing history.
Totally. And interestingly, when it first came out, it wasn't even called C++ late. It had this more straightforward, maybe less poetic name, C with classes.
Tells you exactly what the focus was, though.
It does. But then, in 1983, it got its iconic name, C++AE. And that name itself, it's a brilliant little piece of programming lore.
The plus plural.
Exactly. The plus symbol, that's the increment operator, pulled straight from the C language.
Right. Add one.
It was just a clear, concise statement.
Yeah.
This was C, but, enhanced, incremented, significantly more powerful, especially in how it structured code.
Precisely. And that C with classes name, it really highlights that initial foundational shift. You see, its predecessor, C, was phenomenally powerful, no doubt, but it was procedural.
Step-by-step instructions.
Yeah, focused on sequences of computational steps, functions. C++ introduced this entirely new paradigm, object-oriented programming, OOP.
A big leap.
Huge. These groundbreaking additions, things like classes and objects, they weren't just new features slapped on. They represented a fundamental change in how you could even think about designing software.
Like a conceptual shift?
Totally. Imagine being able to create these digital blueprints for real-world things, a car, a bank account, an image, each with its own data, its own distinct behaviors.
Right, bundling data and actions together.
Exactly. And this allowed developers to model really complex systems in a much more intuitive, more organized way. The benefits were, immense. You got significantly improved code organization, much easier maintenance for large code bases.
Which is critical for big projects.
Absolutely. And crucially, a dramatic increase in code reusability across different projects.
Yeah.
It really redefined the possibilities for software architecture at the time.
That structural thinking is absolutely key.
Yeah.
And speaking of structure, let's explore the basic anatomy of a C++ program itself.
Okay.
When you look at any C++ source file, doesn't matter if it's simple or incredibly complex, you'll typically find a few common components, like its backbone.
The skeleton.
Yeah, exactly. It usually starts with what we call include files. These are essentially directives telling the compiler to pull in external code libraries.
Bringing in tools.
Right. Then you'll often see class declarations, defining those blueprints we just talked about.
The templates.
Following that, you'll see member function definitions. These are the actual implementations, the code for the actions or behaviors associated with those classes.
The doing parts.
And finally, every single C++ program, no exceptions, has a designated starting point, the main function.
And each of those components is vital, They form the skeletal structure that a C++ application is built on.
Can't miss one.
Pretty much. Take include files, for instance. They're your gateway to this vast ecosystem of pre-written, highly optimized code.
Right, so you don't reinvent the wheel.
Exactly. Instead of writing complex routines for, say, talking to the console or doing tricky math, you just hashtag include the right header file.
Like IOStream or SecMath.
Precisely. You leverage existing stuff, save huge amounts of development time, reduces potential errors. Classes, like you said, they provide that fundamental mechanism for encapsulation and data abstraction, creating modular, self-contained units.
Keeping things tidy.
It's very tidy. Member functions. They bring those class blueprints to life. They define the exact actions that objects of that class can perform.
The verbs for the nouns.
Nice analogy. And the main function, that's the absolute entry point. When your C++ program runs, the operating system basically hands control directly to main.
That's where it all begins.
Yep. All subsequent operations flow from there. Without it, your program just wouldn't know where to start.
Okay, to make this really concrete, let's walk through the classic Hello World program.
The rite of passage.
It really is. It's often the very first program anyone writes in C++, and it elegantly shows these fundamental pieces working together.
Simple but effective.
So the program starts with hashtag include IOStream. This line, it's a preprocessor directive, tells the C++ compiler, hey, bring in the contents of the IOStream header file.
Okay.
And the IOStream library. Absolutely vital for any program that needs to do input or output, displaying messages, reading keyboard input. It stands for input-output stream.
Makes sense. IOStream.
Then we have using namespace, STD. Okay, so in C++A, a namespace is like a logical container. It groups related names classes, functions, objects to stop names from clashing.
It's like surnames for code elements.
Sort of, yeah. The STD namespace, short for standard, holds most of the C++ standard library stuff. So by writing using namespace STD, we're basically telling the compiler, look, if I use something like count or send without a prefix, just assume I mean the one from the standard library.
Makes the code cleaner.
Exactly. It lets us use names like count directly, instead of having to write std.count every single time.
Right. Less typing.
Then comes int main. As we just discussed, this is it, the designated starting point for the execution of every single C++ program. Doesn't matter how many other functions or classes you have.
It always starts in main.
Always. The int before main means this function is designed to return an integer value back to the operating system when it's done, usually a status code.
0 for success, usually.
Typically, yeah. Inside main, enclosed in those curly braces we find. Count. Hello world n. Okay, so count. That's the standard output stream object.
The thing that prints to the screen.
Pretty much. Used for printing text or variable values to the console, your display screen. The symbols, people often call them the insertion operator.
Pushing data out.
Exactly. They're used to insert or send the string hello world into the count stream. And that n, that's an escape sequence. It represents a new line character.
So the next thing prints on the next line.
Precisely. When n hits, the cursor moves to the start of the next line. Keeps the output tidy. Finally, we have return 0. This statement, it marks the end of main's execution. And like you said, by convention, returning 0 from main signals to the operating system. Program ran successfully, no errors.
Clean exit.
Clean exit. Any non-zero return value usually means something went wrong.
Got it. And connecting this to the bigger picture, understanding header files goes way beyond just IOStream, right?
Oh, definitely.
I mean, IOStream is fundamental for console I/O, sure, but C++ gives you this rich array of specialized header files, like CMath, that's your go-to for common math functions, squirt for square roots, sin, log.
All the math stuff.
All the math stuff. If you need to work with older C-style input-output, maybe for compatibility, C Studio gives you print, scamps, the C classic.
Exactly. For specific details about floating point number limits, you'd use CFloat. Manipulating strings of characters. CString has functions for copying, joining, comparing strings.
Handy.
Very. And for saving data, persistence.stream is absolutely essential. File streams lets your program read from, write to files on your disk.
Saving user settings, progress.
That kind of thing. Then there's stream for string-based streams. Super powerful for manipulating strings in memory. Parsing data from a string, formatting output into a string.
In-memory I/O.
Basically, yeah. And lastly, cassert. Lets you add assertions checks into your code. Great for debugging. Ensure certain conditions are true. If not, program usually stops. Helps you find bugs fast.
Sanity checks. Pretty much. So looking at the general structure, you'll often see descriptive comments at the top explaining the program. header comments.
For humans, not the compiler.
Exactly. Crucial for teamwork, long-term maintenance. Then your hashtag include statements, bringing in the libraries. After that, you define your functions, your classes, each with their own blocks of statements doing the actual work.
And comments like, my first program are ignored by the compiler, but invaluable later.
Absolutely. And just to reiterate, syn is the standard input stream for reading from the keyboard, the counterpart to count. You use the operator, the extraction operator, with syn to pull data into your variables.
Input-output add.
You got it. That input-output duality is how your program interacts dynamically with the user.
So connecting the dots here.
Yeah.
What this all really highlights is that even these seemingly simple building blocks includes main, basic I/O.
Yeah.
They're the absolute bedrock.
The foundation.
Yeah, the foundation upon which all complex C++ applications are built. Understanding this flow isn't just about syntax. It's the very first step in designing programs that can interact effectively, unlocking that immense power of C++, man.
Well said.
All right, let's transition now into how C++ programs actually do things. We're moving into a deeper look at input-output streams, and then we'll dive into operators, which I kind of like to think of as the verbs of C++ way.
The action words, okay.
So when we talk about I/O streams in C++ way, we're describing the fundamental flow of data, usually bytes, right, within your program. It's basically how your program talks to the outside world and manages internal data.
Communication channels.
Exactly. Two main directions involved. First, input. That's the flow of bytes from a source device like your keyboard, a file, maybe a network connection into your computer's main memory, where your program can work with it.
Like typing your name.
Perfect example. Those characters stream in. Second, there's output, the reverse. Bytes flowing from your program's memory to a destination device, your screen, a printer, another file.
Seeing text appear on the monitor.
That's output in action. Data streaming from memory to the display.
And to manage all these different I/O flows, C++ provides this highly structured hierarchy of header files and classes. It's quite layered.
Right, it's not just IO stream.
Not at all. The foundational IOS header, for instance, has core classes like IOSBase, Basicios, and the underlying stream buffer stuff that all other streams build on.
The base layer.
Exactly. Then you have SStream, specifically for implementing formatted input. That's where Syn gets its smarts for reading different data types.
Okay.
Its counterpart is AWStream, which implements formatted output. Provides the functionalities for count to write formatted data out.
Input stream, output stream.
Makes sense. Right. And IOStream, the one you see all the time, is basically a convenience header. It just bundles IOStream and AWStream together. Your go-to for basic console I/O. Yep. But beyond the console, there's FStream, indispensable for file streams. Gives you class templates like basic stream for input from files, basic offstream for output of files.
For saving and loading data.
That's the one. And a really powerful one, often overlooked, is stream. Provides basic string stream, basic cost string stream, basic cost string stream. Lets you treat strings in memory as if they were input or output streams.
Oh, interesting.
Super useful. Parsing complex text from a string or building a formatted string in memory before writing it somewhere else. Very flexible data handling without touching files directly.
Right.
So fundamentally, your program's interaction boils down to syn for input, count for output. For input.syn variable. The extraction operator pulls data
into the variable
for output.count message or count variable name. The insertion operator sends data out.
To the screen.
Usually, yeah. Mastering these two basic constructs is just paramount for any interactive C++ program.
Okay, so with I/O providing our program's kind of senses, let's shift gears to operators. The verbs. If data and variables are the nouns, operators are definitely the verbs. They're those special symbols that tell the compiler, do this specific mathematical or logical thing.
Perform an action.
Exactly. And C++ is particularly rich in operators. You get a huge toolkit for manipulating data, controlling program flow. We can broadly group them into, arithmetic, logical, relational, assignment, and bitwise operators.
Quite a few categories. Let's quickly hit the highlights and maybe a key insight for each.
Sounds good.
Arithmetic operators. These are your standard math operations, plus addition, subtraction, multiplication, division, and percent modulus, which is the remainder.
Right. Like 7 per 3 is 1.
Exactly. A common thing to watch out for is integer division. If you have 7, 2 with integers, the result is 3. The fractional part just gets dropped.
Right. But 7.0, 2.0 would be 3.5.
Correct. Using floating point numbers changes the game. Also crucial here are plus, plus, increment add 1, and a decrement subtract 1. You see these everywhere in loops and counters.
Very common.
Next, logical operators. Used to combine or modify Boolean conditions, true-false values, is logical OR. The whole thing is true if at least one side is true.
Okay.
And Darren is logical AND. Requires both sides to be true for the whole thing to be true.
Makes sense.
And is logical not to. Just flips true to false, false to true. A key insight here is short-circuiting.
What's that?
Well, in an expression like condition 1 and condition 2, if condition 1 turns out to be false, the program doesn't even bother checking condition 2.
Because the whole A and D can't possibly be true anyway.
Exactly. It already knows the overall result is false. This can save time and sometimes prevent errors if condition 2 involves something risky that should only happen if condition 1 is true.
Clever optimization.
Then, relational operators. All about comparison. Checking the relationship between two values. We've got equality is A equal to B, greater than, less than, greater than, or equal to, less than, or equal to, and allowing for not equal to.
Standard comparisons.
Standard, but the biggest pitfall, especially for beginners, is mixing up the comparison with the assignment.
Oh yeah, putting if x equals 5 instead of if x is 5.
Exactly. That assigns 5 to x, and the condition becomes if 5, which is always true, leads to really subtle, hard-to-find bugs.
Ouch. Been there.
Haven't we all? Okay, assignment operators. They assign values. The basic assigns the value on the right to the variable on the left. But C++ also has shorthand operators, like plus, Manx, Bangles.
The compound ones.
Right. They combine an operation with assignment. So x plus equals 5 is just a shorter way to write x plus 5.
Convenience, mostly.
Mostly convenience, makes code cleaner, sometimes maybe a tiny bit more efficient.
Okay, and the last category.
Bitwise operators. These work directly on the individual bits, the zeros and ones, inside integer types. You have AND, bitwise AND, bitwise OR, bitwise XOR,
Right.
bitwise not or complement, left shift, and right shift.
Sounds low level.
It is. They might seem a bit obscure for general applications, but their insight lies in their power for low-level manipulation. If you're doing embedded systems, graphics, network protocols, or really optimizing for specific hardware.
Then they're useful.
Incredibly useful for things like setting or clearing individual flags stored in bits, or doing super fast multiplication and division by powers of 2 using shifts.
Right. Shifting bits is faster than regular math sometimes.
Yeah.
So connecting these insights, what this all means is that operators are just fundamental, aren't they, for creating dynamic, interactive programs.
Absolutely essential.
Whether you're doing simple math, comparing values, combining complex conditions, these symbols are what allow your program to actually do things. They direct the flow of info, the results of calculations.
With their action verbs.
Exactly. They bring your code to life, let it process, decide, respond. Powerful little symbols.
Very true.
Okay, let's move on to segment 3. Variables, data types, and modifiers. These are really the absolute building blocks for storing and manipulating data within your C++ programs.
The raw material.
Yeah, exactly. At its core, a variable in C++ is just a named location in your computer's memory. You reserve it to store data. Think of it like a specifically sized, labeled box in RAM. A container where you could put different kinds of information. Now, when you name your variables, there are a few rules the compiler cares about. They can have alphabets, numbers, the underscore out.
Okay.
But they must start with an alphabet or an underscore, never a number.
Right. One variable is no good.
Nope. And critically, no blank space is allowed in a variable name. My variable is out. My variable or my variable is fine. And you can't use C++ keywords like int or class as names either.
Reserved words.
Exactly. These rules just help the compiler uniquely identify and manage your data. Keeps things unambiguous.
And the reason these naming rules and the whole concept of variables are so important, it really boils down to data types.
Oh, yes.
Data types are absolutely crucial. They dictate two main things. First, what kind of data can a variable actually hold? Is it a whole number, a single letter, a number with a decimal point, something else?
The nature of the data.
Exactly. And second, just as important, they determine how much memory that variable will take up in RAM.
Which affects performance and memory usage.
Directly impacts your program's footprint and efficiency. Now, C++ has both standard built-in data types, and it lets you create your own user-defined types too. We'll focus now on the 4 main standard types that form the foundation: char, int, float, and double.
Okay, let's dive into each of those, starting with char.
Sounds good.
First up, char. This data type is primarily designed for storing single characters, like A or 7 or at A.
Just one symbol.
Just one. Behind the scenes, characters are often represented by small integer values based on an encoding standard, like ASCII. The source material mentions several variations. Signed char and unsigned char explicitly say if the underlying integer can be negative or only positive, plain char. Its citedness can actually vary between compilers, which is a bit tricky.
Oh, potential portability issue there.
Could be. Then we have radchar for wide characters, needed for characters that take more than 1 byte, like for international alphabets, Unicode.
For handling global languages.
Right. More specifically, char 16th is for UTF-16 characters, char 32T for UTF-32. The need for all these different character types really comes from software being global now. Supporting diverse languages, complex symbols beyond basic English ASCII is just essential.
Makes C++ usable worldwide.
Exactly. Allows it to handle the full range of Unicode characters. Big deal for reach and usability.
Okay, next type.
Next we have int, short for integer. This is for whole number values. No decimals, no fractions. Can be positive, negative, or 0.
Like NACNAS 10, 0, 42.
Perfect examples. Now, the exact range for a standard int can vary depending on the system. 16-bit, 32-bit, 64-bit systems have different sizes. A common example range for an older 16-bit int might be NACNAS 32768 to 32767.
Which isn't huge by today's standards.
Not really. Within the int family, you also find short int and long int. And even long int in modern C++. Short int usually takes less memory, smaller range. Long int and long int use more memory but can store much, much larger integers.
So you choose based on the numbers you expect.
Precisely. Lets you optimize for memory use and the required range for your specific task.
Makes sense. What about numbers with decimals? For
those, we turn to float. This data type is for floating point numbers, real numbers that explicitly have decimal places, like 3.14159 or negative 0.005.
Measurements. Money sometimes.
Exactly. Anything where fractional precision matters. The range for a float is pretty big, typically around plus 63.4838. That's 3.4 times 10 to the power of 38.
Wow, huge range.
Huge range, but, and this is critical, floats have limited precision. They can represent a vast range, sure, but they might not perfectly represent every single real number. You can get tiny rounding errors sometimes.
Because of how they're stored in binary.
Exactly. It's an inherent limitation of representing fractions in binary.
Okay, so if you need more precision,
then you use double. Also a floating point type, like float, but designed for, well, significantly larger real numbers and, more importantly, higher precision.
Double the precision, roughly.
Often, yeah. It can store more digits after the decimal point more accurately than float. Its range is vastly larger, too, roughly 1.7 by 10 at 308 to 1.7 by 10 plus 308.
Astronomical range.
Pretty much.
Yeah.
So if you're doing, say, very precise scientific calculations, financial modeling, dealing with extremely large or small numbers where accuracy is absolutely paramount, double is almost always the way to go over float.
Even though it uses more memory.
Right. Accuracy often trumps memory cost in those cases.
Okay, so char, int, float, double, the basics. What about these modifiers?
Good question.
To further fine-tune these data types, control how they behave, how much memory they use, C++ gives you modifiers. These are special keywords that alter the fundamental nature, the working rules of the standard types.
Like adding adjectives to the nouns.
Kind of. They let you be remarkably specific about a variable's memory allocation and how its values are interpreted. Two main categories. First, size modifiers.
Like long and short.
Exactly. They literally adjust the memory allocated, which in turn impacts the range of values it can hold. Long generally increases the size, like long int or long double. Short usually decreases it, like short int.
So an int might be 4 bytes, short int maybe 2 bytes, long int maybe 4 8 bytes?
Precisely. Depends on the system, but that's the idea. This granular control is essential in memory-tight situations like embedded systems, or just when you need to guarantee a variable can hold a specific range without overflowing.
Okay. And the second type of modifier?
Sign modifiers. These influence whether a data type can store positive values, negative values, or both.
Signed and unsigned.
You got it. If you use signed, the variable can hold both positive and negative numbers, which is actually the default for most integer types, like int, if you don't specify anything.
Right.
But if you explicitly use unsigned, you're telling the compiler, this variable will only store non-negative values, 0 and positive integers.
Why would you do that?
Well, the critical insight is, by giving up the ability to store negative numbers, you effectively double the positive range the type can represent.
Ah, because the bit used for the sign can now store more value.
Exactly. That sign bit becomes available for magnitude. Incredibly useful for things like counters, array indices, bit flags, anywhere a negative value just doesn't make sense.
Right. You can't have a negative array index.
Typically not, no. This raises an important question, though. Why are we being so meticulous about differentiating these types and modifiers?
Yeah, seems like a lot of detail.
The practical implications are significant. Choosing the right data type and modifier directly impacts your program's memory efficiency. Using short int instead of long int when you don't need the range saves valuable memory. Crucial for embedded systems or huge applications processing tons of data.
Makes sense.
Furthermore, it's about data integrity. By picking the type that most accurately represents the data you intend to store, you prevent nasty, subtle bugs, like integer overflows, where a number gets too big for its type and wraps around.
Often to a negative number, unexpectedly.
Exactly. Or precision loss in floating point math. It forces you, the programmer, to be precise about your data right from the start.
So, to summarize them, variables are labeled storage bins in memory. Data types tell those bins exactly what kind of info they can hold and how big they are, making sure data is stored correctly.
Right.
And modifiers give us that fine-grained control to optimize the bins for size and range and whether they handle negative values.
Precisely.
Together, they're the fundamental elements for accurately handling, manipulating, and optimizing all the information within your C++ program.
Couldn't have said it better myself.
All right, let's transition into segment 4. Navigating program flow with control structures. This is where programs really start to, think, make intelligent decisions, perform repetitive actions.
Getting to the logic now.
Exactly. Control structures are basically the statements that dictate the sequence of a program's execution. Without them, your C++ code would just run line by line, top to bottom, predictable, linear.
Pretty boring for complex tasks.
Totally boring.
Yeah.
But control structures, they introduce incredible flexibility. They empower your program to make decisions based on conditions, execute blocks of code repeatedly, or even jump to different sections entirely.
They tell the program what to do and when, based on what's happening.
Exactly. Based on dynamic input or internal state. We can generally categorize them into 3 main types. Selection statements for decision-making.
Like if and switch.
Right. Iteration statements, usually called loops for repetition.
Or follows. Do while.
Yep. And jump statements, which alter the normal flow unconditionally.
Break, continue, go to.
You got it.
Okay, let's start with selection statements. These are all about letting your program choose different paths based on conditions. The first, the most fundamental, is the if statement.
The classic.
The classic. Its purpose is simple. Execute a specific block of code only if a specified condition or expression evaluates to true.
If this is true, do that.
Basically, the syntax is if expression. Let's look at that example. Int a equals 400. Int b equals 800. If ba count b is greater than a.
Okay, so b800 is greater than a 400.
Right. So the condition ba is true. Therefore, the code inside the curly braces executes, and it prints b is greater than a.
And if b was 300?
Then ba, 300, 400 would be false, and the count statement inside the braces would simply be skipped. Control would just continue after the if block.
Simple enough.
Building on that, we have the if-else statement. This extends the if by providing an alternative path. It executes one block if the expression is true and a different block if the expression is false.
If true, do this, otherwise do that.
Exactly. Guarantees one of 2 paths is always taken. Syntax.s expression, so take this example. Int a equals 100, int b 200. If ab count a is greater, if a is not greater than b, 200, so ab is false.
Correct. Since it's false, the code inside the else block executes and it prints b is greater than a, ensures a clear decision is made. Got it. Handles both possibilities.
Now, for more complex multi-way branching, especially when you need to choose from several options based on the specific value of one expression, C++ gives us the switch statement.
Instead of nested if-else statements.
Often cleaner than lots of nested if-else-ifs, yeah. It efficiently lets a program run different code blocks depending on the evaluated value of an expression, usually an integer or character expression.
Okay.
The syntax looks like switch expression, case value 1, statements break, case value 2, statements break, default, statements break.
Lots of keywords there. Case, break, default.
Let's break down the day number example. User enters a number 1 to 7 for the day of the week. cpp.intDay, synday, switch day, case 1.count Monday, break, case 2, count Tuesday, break, case 2, cases 3 to 6, default, count Sunday, break, handle 7 or invalid input, default.
Okay, so I entered 2.
Switch evaluates day, which is 2. It finds a match with case 2, executes count Tuesday. Then, crucially, it hits the break statement.
What does break do here?
Break is vital. It immediately exits the entire switch statement. Without break, C++ would exhibit fall-through behavior.
Fall-through?
Yeah, it would continue executing the statements in the next case, case 3 in this example, and the one after that, until it hits a break or the end of the switch. Usually not what you want.
So break stops it after the matching case.
Exactly. Forgetting break and switch cases is a super common bug. The default case acts as a catch-all. If none of the specific case values match the expression, the default block runs.
Handy for errors or fallback options.
Very handy. Okay, moving on to iteration statements. Loops. These let your program repeat a block of code multiple times.
For processing lists, running simulations, etc.
Exactly. The first is the for loop. Generally the best choice when you know or can easily figure out the exact number of times you want to repeat something.
Like, do this 10 times.
Precisely. Its typical syntax is for initialization, condition, increment statements. Let's look at the example iterating 1 to 4 for int ii 1i5 i++, count looping.
Okay, 3 parts in the parentheses.
Right, here's the flow. 1, initialization, int I equals 1. The loop variable is created and set to 1. This happens only once at the start. 2, condition, I5. Before each potential iteration, this is checked. If true, the loop body runs. If false, the loop terminates. 3, statements, the code inside executes. 4, increment, I++. After the loop body finishes, this runs, I increases by 1.
So it runs for I1, I2, I3, I4, then I becomes 5, I5 is false, loop stops.
Exactly. Prints messages for 1, 2, 3, and 4. The for loop neatly packages initialization, condition checking, and updating the counter all in one line. Very common, very readable for fixed iterations.
Got it. What's next?
Next up, the while loop. This loop repeats a block of code as long as a specified condition remains true. It's great when you don't know the exact number of iterations beforehand.
Like, keep doing this until the user types quit.
Perfect example. The loop continues until some condition changes. The basic syntax, while condition. Let's analyze a decrementing number example. CPT n tn sin n. Assume n 0, while n 0. Count value is nn. Count value is n. Crucial step. Count value is.
Aww.
Okay, if I enter 4, while checks n0, 0 is true. It prints value is 4. Then n makes n become 3. Loop repeats. Checks 0, 0, true. Prints 3, n becomes 2. Checks 0, true. Prints 2, n becomes 1. Checks 1, 0. Prints 1, n becomes 0.
Then it checks 0, 0, which is false.
Exactly. The condition is now false, so the loop terminates. Control jumps to the count loop finished line. The critical thing with while loops is ensuring something inside the loop eventually makes the condition false. Otherwise,
infinite loop.
Infinite loop. Program hangs. You have to make sure the condition can change.
Right. Okay, one more loop type.
One more main one. The do while loop. Its defining feature is that its code block is guaranteed to execute at least once.
Even if the condition is initially false.
Yes. The condition is checked after the first execution. After that first run, it behaves just like a while loop, repeating as long as the condition stays true.
Interesting. Test happens at the bottom.
Exactly. Syntax.do statement, while condition. Notice the semicolon after the while condition. Let's look at the hello KF, oops, example, cpp.intn, sin in, number of times to display .do count, oops, n 0.
So if I enter 0 for n?
Even if you enter 0, the do block runs once. Oops gets printed, then the n becomes -1, then the while n0 condition -10 is checked. It's false.
So the loop stops after just one run.
Exactly. If you entered 3, it would print oops 3 times. This execute at least once guarantee is the main reason you'd choose do while over while. Maybe for validating input where you need to get the input first before checking it.
Okay, that makes sense. Now for the jump statements.
Right, jump statements. These let you transfer control unconditionally, sometimes quite abruptly. First break. We saw in switch. It also works in loops. For while, do while.
What does it do in a loop?
Same idea. Immediately terminates the innermost loop it's inside. Control jumps to the statement right after the loop finishes. Syntax is just break. In the example, CPP for int I 0 I 10 I++. Count counter if I5, count counter break, exit loop when I hits 5, count counter at counter count, exited loop.
So it prints 0, 1, 2, 3, 4, 5, and hits the if.
When I is 5, if I5 is true, break. Executes, the for loop stops immediately, skips iterations 6, 7, 8, 9, control jumps straight to count, exited loop.
Okay, immediate exit. Then there's go to.
Go to, the controversial one. It transfers control directly to a labeled statement somewhere else in the code. Syntax is go to label, and you mark a destination with label.
Like a bookmark you can jump to?
Pretty much. In the alphabet example, if you enter 1, it prints you chose A, then go to exit program, jumps execution straight to the line labeled exit program, skipping cases B and C entirely.
Why is it controversial?
Because it can lead to what's called spaghetti code. It makes a program's logic incredibly hard to follow, debug, and maintain because it bypasses the nice structured control flow of loops and ifs.
Jumps can go anywhere, making it confusing.
Exactly. Modern C++ programming strongly discourages go-to. Use it only in very rare specific situations where it genuinely simplifies things, and even then, be very careful. Structured programming is almost always better.
Good advice. Last jump statement.
Continue. Unlike break, which exits the loop, continue just skips the rest of the current iteration.
It doesn't end the loop.
No, it just jumps immediately to the next iteration, skips whatever code comes after, continue within the loop body for that one cycle. Syntax is just continue. Let's look at the example, skipping a 13 CPP into 9, UF A plus 1. Important. Update A here too. A plus 1. Important. Continue. Skip the rest for a 13. A count value A plus 1. Count value with a 15.
Okay, so it prints 9, 10, 11, 12. Then it becomes 13.
If A is 13 is true, A is incremented to 14, then continue, executes. This immediately sends control back up to the while, a 15 check.
Ah, so it skips the count and the second AB key plus 1 for the iteration where it was 13.
Exactly. So 13 never gets printed, but the loop doesn't end. The condition 1415 is true, so it continues, prints value. 14A becomes 15, the condition 1515 is false, and then the loop terminates. Continue is for bypassing specific parts of a loop cycle under certain conditions.
Got it. Skip this round, move to the next.
Precisely.
So connecting all these pieces, wow. Control structures really are the backbone of dynamic programs, aren't they?
Absolutely. They're what makes software intelligent.
They let your code think by making decisions, if switch, act, by repeating operations for while, do while, and respond intelligently to different situations.
And jump around when needed, carefully, break, continue, maybe go to.
Right. Mastering these statements lets you create way more powerful, flexible, intelligent programs than just simple linear instructions could ever manage. They really empower your code to adapt and perform complex tasks.
Definitely unlocks the potential.
Now let's move into segment 5. Functions, classes, and objects. These are really the foundational pillars of object-oriented programming in C++, concepts that truly revolutionize software design.
Yeah, this is where C++ really starts to differentiate itself from C.
Let's start with functions. Think of functions as separate self-contained modules, blocks of code designed to do one specific task within your program.
Little reusable machines.
Exactly. The benefit is huge. First, they let you break down a big, complex program into smaller, more manageable logical chunks. Makes code way easier to understand, debug, maintain.
Divide and conquer.
Totally. But even more powerfully, functions promote code reusability. You define the logic, say a calculation, inside a function just once. But then you can call that function, execute it multiple times from different places in your program.
Saves you writing the same code over and over.
Which saves time, reduces errors, makes updates easier. Huge win.
Indeed. And your main function can then act as sort of an orchestrator, right? Calling these different functional blocks to achieve the overall goal.
Like a conductor leading the orchestra sections.
Nice. In C++ then, we mainly deal with two types of functions. First, library functions, also called predefined functions. These are already written, compiled, and tucked away in standard header files that come with your C++ compiler.
Like squirt or count.
Exactly. You don't write their code. You just #include the right header file, cmath for squirt, iostream for count, and then you can just call them and invoke them directly.
Convenient.
Very. A classic example is ceil and floor from cmath.ceiln finds the smallest integer greater than or equal to n, rounds up.
So ceil 3.2 is 4.
Right. And floor n finds the largest integer less than or equal to n, rounds down.
So floor 3.7 is 3.
Exactly. In the example code, you #include cmath, get a number n, and then just call std.ceiln and std.floorn. All the tricky logic for rounding correctly is already built into the library. Reliable, saves you effort.
Okay, so library functions are built-in tools. What's the other type?
The second, and arguably more flexible type, are user-defined functions. These are the functions that you, the programmer, design and create.
To solve our specific problems.
Exactly. To encapsulate custom logic, abstract away complex steps into a single callable unit. Unlike library functions, you must provide the definition, the code, for what these functions do. But you don't need a special header file to call them since their definition is part of your own project.
Okay. How do we define them?
The general syntax involves specifying the return type, what kind of value the function sends back, like int or void if nothing, the function name, and then in parentheses, a list of parameters it accepts, the input data it needs, followed by the function body in curly braces containing the actual code.
Got it.
Let's look at that mult function example, CPP, hashtag include iostream, int mult, int ig, int b, prototype declaration dot int main, into xy, synxy, tout xy, count product, mults xy, count product dot return 0, count product dot int mult, into int b, definition, count product dot return, count product dot duck.
Okay, I see the mult function defined at the bottom. But what's that line int mult, int a, int b, before main?
Ah, that's crucial. That's a function prototype declaration, or forward declaration. It tells the compiler about the function, its name, mult, return type int, and parameter types, int, before main tries to call it.
Why is that needed?
Because in this example, main is defined before the actual definition of mult. Without the prototype, when the compiler reads main and sees the call mult xy, it wouldn't know what mult is yet, and it would give an error.
Ah, so the prototype promises the compiler, don't worry, this function exists, I'll define it later.
Exactly. Then the actual logic, return a b, is provided in the definition after main. When mult xy is called in main, it passes the values of x and y, the function calculates the product and returns it. This separation of declaration, prototype, and definition is very common in larger C++ projects for better organization.
Makes sense. Okay, from functions, let's build up to classes. You said this is a core C++ concept.
Absolutely core. And one of its most powerful features. A class is basically a technique to hold related data structures and functions together, bundled into a single unit.
Like a custom data type.
Exactly. It's a blueprint, a template, that lets you create your own separate user-defined data types. So instead of just basic ints or chars, you can define a complex type representing a real-world thing, a car, a student, an image.
Right.
This leads us to a key OOP principle. Encapsulation, bundling the data, what the thing is, and the methods or functions, what the thing does together, and often hiding the internal workings.
Okay, how do we define a class? When you define a class, you start with the keyword class, followed by the name you give it, like class image. The body goes inside curly braces. And crucially, unlike functions, a class definition must end with a semicolon after the closing brace.
Ah, easy to forget that semicolon.
Oh, very easy. Inside the class, you define both data members' variables that hold the class's state, its properties and member functions, the behaviors, the operations that can be performed on that state.
Data and actions together.
And a critical aspect here are the visibility labels, private and public. These control who can access the members of your class.
Access control.
Right. When you declare data or functions under private, they can only be accessed from inside the class itself by its own member functions. This is fundamental to encapsulation. It hides the internal details, protects the data's integrity.
Keeps outsiders from messing with the internals directly.
Exactly. In contrast, stuff declared under public is accessible both inside and outside the class. These public members form the controlled interface, the gatekeepers, through which the rest of your program interacts with objects of this class.
The public API, essentially.
That's a good way to put it.
So, the general syntax for declaring a class looks something like this. CPP class, my class name.
Private data members, variables. Private member function declaration.
Public data members, less common, usually functions. Public member function declarations, the interface. The crucial semicolon.
Okay.
Let's look at that image class example again. It's a fantastic illustration. CPC class image.
Int width, int height, char pixels, pointer to the actual image data.
Int get width. Getters. Char get pixel, int x, in y. Void set pixel, int x, in y. Char value. Setter. Void save. Char file name. Action.
So width, height pixels are private, hidden away.
Exactly. They can only be directly touched or changed by functions within the image class itself. This enforces encapsulation. It bundles the image's data with height pixels with the methods that operate on it and restricts direct, uncontrolled access to that raw pixel data. Protects the image data's integrity.
So you can't accidentally corrupt the image from outside.
But much harder to, yeah. The public members get width, get height, get pixel, set pixel, save. These are the carefully designed functions that provide the controlled interface for interacting with an image object. You don't fiddle with the pixels array directly. You call set pixel or get pixel.
Which can include validation or checks.
Precisely. They ensure proper handling. What's fascinating here is how the separation of private internals from the public interface makes code so much more robust, easier to manage, and less error-prone, especially in large systems.
Okay, so a class is the blueprint. How do we actually build something from it?
Ah, good question.
That's where objects come in.
Right.
An object is an instance of a class.
Exactly. The relationship is like a variable to a basic data type. Just like int x declares x as a variable of type int if you have class product.
Right.
My product declares my product as an object of the product class.
So the object is the actual thing created from the blueprint.
Yes. An object contains the actual properties, data members, and behaviors, member functions, defined by its class blueprint. And crucially, when you create an object, it occupies memory to store its own unique state, its own set of data values. So objects are the concrete, living realizations of your abstract class blueprint. When you create one, memory gets allocated for it, holding its own distinct set of data based on the class definition.
Like building a specific car from the general car blueprint.
Perfect analogy. You can declare objects just like variables. Product X makes one product object named X. You can also declare multiples, product X, Y, Z.
Okay.
The general syntax is straightforward. CPP class, my class members, my class of J1, declares obj1 as an object instance of my class of J2, of J3, declares multiple objects. Now you can use obj1 of J2 of J3, rep return 0.
So my class is the blueprint. Obj1, Obj2, Obj3 are the actual things built from it.
Correct. When Obj1 is created, memory is allocated according to my class's design. It's ready to store its own unique data and execute its member functions. Each object, Obj1, Obj2, Obj3, gets its own separate copy of the data members defined in the class. They become independent entities your program can work with.
Right, so changing Obj1's data doesn't affect Obj2's data.
Exactly. Unless they're interacting in some specific way, they are independent.
Okay, so connecting these concepts. Functions let us modularize code, make it reusable. Classes give us this powerful way to define our own complex data types, bundling data and behavior together in encapsulation.
Right.
And objects are the living, breathing instances of those classes, the actual entities our program creates and works with in memory.
The concrete things.
Together, functions, classes, objects. They form the very core of object-oriented programming, leading to much more modular, reusable, organized, and ultimately more maintainable and scalable code.
That's the promise of OP, and C++ delivers it powerfully.
Now, let's keep building on these OOP concepts in segment 6. We'll dive deeper into exactly how you define those crucial member functions and then unlock the immense power of inheritance.
2 more huge pieces of the OOP puzzle.
Definitely. So we've established member functions are declared inside a class, and they operate on that class's data. But when you write the actual code for them, they're implementation. C++ gives you 2 main options. You can define them either right inside the class definition or outside the class definition.
Yeah, you have a choice there. Each has its place.
Let's look at defining them inside the class definition first. This is often more compact, maybe more straightforward, especially for simple functions.
Shorter ones. Yeah.
In this method, the function's entire body, its logic, is written directly within the class's curly braces, usually right after its declaration.
Like in the product class example provided, CPP class product and product ID, float price.
Void get data, int A, float B, declared here but defined elsewhere. Void, put data. Void, defined right here, inside the class. std.ad, product ID. ID, product ID, product ID price. With price, std.nag, std, oh.
Okay, so put data's code is right there inside product.
Exactly. Its implementation, printing the ID and price, is embedded directly in the public section.
Inline. What does that mean?
It's basically a hint to the compiler. It suggests that it might be beneficial to substitute the function's code directly wherever it's called, instead of doing a formal function call jump.
Ah, potentially faster by avoiding the call overhead.
Potentially, yes. Minor optimization, especially for short, frequently called functions. The compiler isn't forced to inline it, but it often will if it makes sense. So defining inside is good for short, simple functions.
Okay. What's the alternative?
The alternative, often preferred for larger or more complex member functions, is defining them outside the class definition.
Keeping the class definition cleaner.
Exactly. In this approach, you first declare the function inside the class, like getData was declared in product, just the signature, no body. Then you provide its full definition separately, outside the class's braces. typically in a corresponding .cpp source file.
Okay, but how does the compiler know which class that outside function belongs to?
That's where the scope resolution operator comes in. You must use it. It explicitly tells the compiler which class the function is a member of.
Like class name, function name.
Precisely. The syntax is return type class name, function name parameter declarations, function body, or thing. Let's analyze the cube class example. cpp.classCube.
Inside, int get volume. Inside volume. Declared inside. Defined outside using scope resolution operator.
Return side set.
Okay, so get volume is declared inside cube, but the code return side is outside.
Right. And the cube part before get volume explicitly links that definition back to the cube class.
Yeah.
Now, this raises the question, why choose one over the other?
Yeah, when would you define outside?
Defining functions outside can significantly improve readability, especially for big classes. The class definition itself stays concise, acting more like a clean interface summary.
Like a table of contents.
Good way to put it. It also helps with separation of concerns. Often the class definition interface goes in a header file, hr.hpp, and the implementation's definitions go in a source file, .cpp. This is standard practice for larger projects, helps manage compilation, dependencies, etc.
Okay, makes sense for bigger code bases. Now for member functions, let's make that big leap to inheritance. You called it one of the most fundamental OOP features.
Absolutely. It's a cornerstone of OOP. Inheritance is this sophisticated technique that lets you reuse existing classes and establish clear hierarchical relationships between them. It models real-world relationships.
Like a dog is an animal.
Perfect example. In essence, inheritance lets one class acquire or inherit the properties, data members, and characteristics, member functions, of another class. You don't have to rewrite common stuff.
Built-in reuse.
Exactly. Now, the terminology is important. The class that gives its properties is the parent or base class. The class that receives or inherits is the derived sub or child class.
So family tree for code.
Pretty much. The child automatically gets traits from the parent, but can also add its own unique features or modify inherited ones.
Oh, okay. Are there different kinds of inheritance?
Yes. C++ offers a flexible model with 5 distinct types, allowing for diverse class structures. 1, single inheritance, simplest form. 1 derived class inherits from just one base class.
Yeah.
1 parent. 2, multiple inheritance. A single derived class inherits from 2 or more distinct base classes. Amphibious vehicle, muscle car plus boat.
Whoa, multiple parents.
Yep. Combines features from multiple sources, can get complex. 3, multi-level inheritance. A chain. Class C inherits from B, and B inherits from A. Poodle, dog, goat, and ass animal.
Like grandparents.
Exactly. C gets features from B and indirectly from A4. Hierarchical inheritance. Multiple drive classes inherit from a single base class. Vehicle, mass car, vehicle, motorcycle, vehicle, truck.
One parent, many children.
Right. One base blueprint spawns several specialized versions. 5, hybrid inheritance. A mix of the above. Often combining multi-level and multiple inheritance for complex designs.
Okay, lots of options. How do we actually write it?
The general syntax looks like this. Class name, access mode, base class name, members of subclass.
That's access mode.
That's crucial. It can be public, private, or protected. It controls how the inherited members from the base class can be accessed within the derived class and by code outside the derived class. Public inheritance is the most common. It basically means public members of the base class remain public in the derived class. It preserves the base class interface.
So the is-a relationship holds publicly.
Exactly. Let's look at the cars and bike example for single inheritance. It shows this well. CPP class. Cars. Base class. Void display cars info. Bike class. Bike public cars. Derived publicly inherits from cars. Bike's own member. Void display bike info. Bike outcome. Object of derived class. Kappa B wheels. Accessing inherited member. Wheels is 4. Cal B tires. Accessing own member. Tires is 2. B display cars info. Can call base class function. B display bike info. Can call own function. Return 0. Okay, so cars is the base. Bike derives from it using public cars.
Right. This means bike publicly inherits all public and protected members of cars. So when we create a bike object B, it automatically has access to wheels and display cars info from cars, plus its own tires and display bike info.
So B wheels works and gives 4, even though wheels isn't defined directly in bike.
Exactly. It got it from cars. The output shows B wheels is 4 and B tires is 2. The derived class seamlessly gains properties from its base.
That's powerful for reuse.
Incredibly powerful. Connecting this to the bigger picture, inheritance is the cornerstone of code reusability. Define common stuff once in a base class, and all derived classes get it automatically. No rewriting.
Reduces redundancy, streamlines development.
Massively. Makes code bases much more manageable, and it beautifully models those real-world is-a relationships. A bike is a kind of vehicle. A call is a kind of vehicle. If vehicle was the base, both would inherit common things. Speed, color, move method, while adding their own specifics. Kickstand for bike, trunk for car. Leads to more organized, scalable, maintainable programs. Crucial for big software.
So connecting these ideas. Member functions let classes do things. Define behavior.
Give life to objects.
And inheritance is this masterful trick for organization, reuse, establishing hierarchies.
Building families of related classes.
These two concepts are just fundamental for building complex, efficient, maintainable, object-oriented systems.
Absolutely central to OOP in C++ Ray.
All right, now we arrive at segment 7, polymorphism, the power of many forms in C++ Ray. Sounds intriguing.
It really is. Polymorphism is another strategic, incredibly powerful feature of OOP. The name itself, polymorphism, literally means having many forms.
Poly, many, morph form. Okay.
And this concept really shines when you have a hierarchy of classes related by inheritance, like we just discussed. It allows objects of different derived classes to be treated as objects of a common base class.
Okay, using a base class, pointer, or reference.
Exactly. But here's the magic. Even when treated as the base type, they still behave according to their specific derived type at runtime. This flexibility is a game changer for adaptable software design.
So the same code can work with different types of objects and get different results.
Precisely. C++ implements two main types of polymorphism. First, compile-time polymorphism, also called static binding or early binding.
Decided when compiling.
Right. The specific function to call is determined by the compiler at compile time. This usually happens through things like function overloading, same function name, different parameters, or operator overloading, giving operators like plus custom meanings for your classes. The decision is locked in before the program runs.
Okay, what's the other type?
The second type is runtime polymorphism, also called dynamic binding or late binding. Here, the specific function call is resolved at runtime.
While the program is actually running.
Yes. The program decides which version of a function to execute based on the actual type of the object it's currently working with, not just the compile time type of the pointer or reference pointing to it.
How does it do that?
Primarily through the use of virtual functions in base classes, combined with using pointers or references to those base classes to refer to derived objects. This is what enables the true many forms behavior.
The virtual keyword is key then.
Absolutely key for runtime polymorphism. Let's analyze that classic example using shapes, rectangle, and triangle. We need to pay close attention to virtual. Here's the corrected code structure. CPP class shapes.
Constructor area, local mon code constructor area. Important. The aforementioned double area, cross entry shapes and rect. Cart triangle area return to a trochal area. Cart triangle area shapes and rect. Cart triangle area shapes. Direct is to turn in trictor, turn trictor, return with conforgo. Cart triangle area, commute cart triangle area port calls which area return infect by rectonus and trigia. Cart triangle area shapes important. Cart triangle area churned with hitrio, cart triangle area. Return 0 wepago. Return 0. Count triangle area. Cost with which area? Count triangle area. On returned cute.
Okay, so we have a base class, shapes pointer, shapes PTR. First it points to a rectangle, then it points to a triangle. Both times we call shapes PTR.
Exactly. Now, because area is declared virtual in the shape space class, C++ performs runtime polymorphism.
So it doesn't just call the shapes.area version?
No. When shapes p-area is called the first time, the program checks, at runtime, what actual type of object is shapes PR pointing to right now. It sees it's pointing to a rectangle, so it calls rectangle.area.
And prints rectangle area.
Correct. Then, when shapes ptar is made to point to the triangle object tria, and shapes p-area is called again, the runtime check says, now it's pointing to a triangle, so it calls triangle.area.
And prints triangle area?
Exactly. This is the magic. The same line of code, shapes p-area executes different versions of the area function depending on the actual object being pointed to at that moment.
What if area wasn't declared virtual in shapes?
Good question. Without virtual, C++ would default to static binding. It would look at the type of the pointer, shapes, at compile time and say, okay, I'm calling the area function belonging to shapes. Both calls would then execute shapes.area, printing parent class area default both times. regardless of the actual object type.
So virtual enables the dynamic dispatch.
Precisely. It tells the compiler to set up the mechanism, usually involves something called a virtual table or vtable, to allow this function call resolution to happen at runtime based on the object's true type.
Wow. Okay, what's the big advantage of this?
What's truly fascinating and powerful here is the incredible flexibility and extensibility it unlocks. It lets you write generic code that interacts with objects through a common base class interface, like shapes in the array function, without needing to know the specific derived type until the program is running.
Like that drawing application example you mentioned.
Exactly. Imagine a function process shape. Double A is area. You can pass pointers to rectangles, triangles, circles, if you added that class later, into this single function. And inside S area will always call the correct area function for whatever shape S happens to be pointing to at the time.
Without changing process shape at all when you add circle.
Not one bit. You can add new derived types to your system without modifying existing code that uses the base class interface. This fosters highly adaptable, robust, easily maintainable software architecture, indispensable for large, evolving projects.
That's a massive advantage. Any downsides?
There's a very slight performance overhead compared to a direct function call because of the runtime lookup needed using the B table. But honestly, for most applications, this cost is negligible compared to the huge design benefit polymorphism provides.
So connecting these dots, polymorphism, especially runtime polymorphism with virtual functions, gives C++ objects this incredible ability to take on many forms, behave differently based on their actual type and context, even when handled through a generic base class pointer.
Yeah, that's the essence.
This unparalleled flexibility makes programs more adaptable to change, more extensible for new features, and ultimately way more robust when dealing with complex systems and unpredictable requirements.
It's truly a cornerstone of modern, scalable software engineering in C++.
Absolutely fantastic. And just like that, wow, we've navigated a truly foundational deep dive into C++ programming.
We covered a lot of ground.
We really did. From its ingenious origins with Bjarne Stroustrup, that evolution from C with classes. We unpacked the basic structure, dove into I/O streams, explored that versatile toolkit of operators.
The building blocks?
Then we built up understanding with variables, data types, modifiers, how C++ handles information precisely. We saw how to control program flow with selection, iteration, jump statements, making programs think.
Adding the logic.
And finally, we plunged into those powerful OOP concepts. Functions for modularity, classes and objects for blueprints and instances, member functions for behavior, inheritance for reuse and hierarchy.
And polymorphism for that amazing flexibility.
Exactly. This deep dive, it was really crafted to be your shortcut, to becoming truly well-informed about the core of C++ play.
And this raises, I think, an important question for you, our listener. How might these core C++ concepts be applied to solve real-world problems you encounter in your work, your studies?
Yeah, how can you use this?
Or maybe, how do these C++ paradigms connect to other programming languages or systems you already know? Seeing those connections can really deepen your overall understanding of software design.
That's a great point.
Understanding these fundamentals, it's really the true starting point for building complex, efficient, well-designed software systems. And, we at Knowledge Flow, we're extremely passionate about education. We really encourage you to always seek knowledge, read books online, offline for continuous learning.
Keep that curiosity going.
Absolutely. Knowledge Flow offers a really wide variety of topics. Engineering, science, business and management, school books for students, learners of all levels. You can actually find more than, I think it's over 100 popular education books at the best prices in India, right there on Knowledge Flow. It's a great resource to continue your learning journey and further unlock new possibilities in development.
Absolutely. Continuous learning is key. Thank you so much for joining us on this deep dive into C++ programming presented by Knowledge Flow.
It was a pleasure.
We really encourage you, keep exploring, keep learning, and we definitely look forward to having you join us for the next deep dive. Until then, keep those intellectual gears turning.